Transient response specifications. Hello everyone. In this video, we're gonna solve the 3 exercises related to transient response specifications in control systems. Let's go to them. Exercise number 1 says that for the system described by this block diagram, zeta is 0.6 and Wn 5 radians per second. With this data, the exercise wants us to calculate the rise time, the peak time, the maximum overshoot, and the settling time. Okay, my friends, this is the question. Let's go to the solution. From the values of zeta and Wn, we get Wd is equal to Wn times the square root of 1 minus zeta squared, which is 4 radians per second. Okay? Else, we find that sigma is equal to zeta Wn, which is equal to 3. Okay? We're going to need these values to calculate the following. Let's go. The first, the rise time, Tr. The rise time is pi minus beta over Wd. But how do we calculate beta? Beta can be calculated as here is J Wd, and here negative sigma. Beta is this angle here. Okay? And then beta is the inverse tangent of Wd over sigma. We use this value here and this value here, and we find that beta is 0.93 radians. Okay? And if we use this value here, we find 3.1416, an approximate value for pi, minus 0.93 divided by Wd, which is 4. And then we get that the rise time is 0.553 seconds. This is our first response. The rise time is 0.553 seconds. Okay, now let's calculate the peak time. The peak time can be easily found by using the expression Tp is equal to pi divided by Wd, which is equal to 3.1416 divided by 4. Again, an approximate value for pi and we get that the peak time is 0.78 seconds. Okay? Easy. Once we have the value of WD, the peak time can be easily found. Now let's calculate the maximum overshoot. The maximum overshoot, MP, is equal to e raised to the power of minus pi sigma over WD, which is e raised to the power of minus 3/4 of pi, which is approximately equal to 0.0995. Or, if you prefer, this in percentage, MP in percent is equal to 9.5%. Okay? This is the maximum overshoot. And to finish, we are going to calculate the settling time. The settling time, TS, for the 2% criterion, 2% criterion, we find that TS is equal to 4 over sigma, which is 4 over 3, which is 1.33 seconds. And for the 5% criterion, we find that TS is equal to 3 over sigma, which is 3 over 3, which is 1 second. Okay, my friends? This is the settling time for this control system. This is all for exercise 1. Let's go now to exercise 2. Exercise 2 says that the step response of a second order system is as shown by the graph. With this data, the exercise wants us to calculate the value of the damping ratio. Okay, my friends, this is the question. Let's go to the solution. To find the value of the damping ratio, we are going to use the expression of the maximum overshoot. The maximum overshoot can be calculated by this expression, pi zeta divided by 1 minus zeta squared, the square root of it all. And you can see that the maximum overshoot is 1.25 minus 1, which is 0.25. Okay? If we take the natural logarithm of this part and this part, we get minus pi zeta divided by the square root of 1 minus zeta squared equal to the natural logarithm of 0.25, which is minus 1.386. Okay? We are going to square both sides now. We're going to square here and here. Following this procedure, we get that pi zeta squared divided by 1 minus pi squared zeta squared divided by 1 minus zeta squared is equal to 1.92. From this we get that zeta, the damping ratio, is equal to 0.29. Okay? Easy, isn't it? The catch here is to remember the expression for the maximum overshoot. The rest is easy. Okay, my friends, this is everything for exercise 2. Let's go now to exercise 3. Now let's go to exercise 3. Exercise 3 says that for the system modeled by the block diagram on the board, what is the steady state error to the unit step input? Okay, my friends, this is the question. Let's go to the solution. The first step that we're going to take will be to come up with the transfer function of this block diagram. The closed loop transfer function can be calculated as follows. If we have A of S here and B of S here in a feedback loop, the transfer function C of S over R of S will be C of S over R of S equal to A over 1 plus AB. Okay? This is what we are going to use here to calculate the closed loop transfer function of this block diagram. And from the transfer function, we are going to calculate the steady state error. Let's go. Let's do it. The closed loop transfer function will therefore be C of S over R of S equal to 1 over S squared plus 10S 1 plus 10S over S squared plus 10S. Okay? And this gives 1 over S squared plus 10S plus 10. This is the closed loop transfer function of this block diagram. We are going to use this to calculate the steady state error. The error transfer function may be obtained as E of S is equal to R of S minus B of S. E of S, the error, is here, and B of S is here. Okay? But B of S, as you can see, is 10 times the output because it is a feedback loop here. Okay, 10 times C of S. Then we substitute it here. Okay, it is R of S minus 10 times C of S. Okay? And if we divide both sides by R of S, we get E of S over R of S equal to 1 minus 10 times C of S over R of S. C of S over R of S is our closed loop transfer function. Then it is 1 minus 10 S squared plus 10 times S plus 10. Okay? And we are going to multiply this by this and subtract 10 to arrive at the final expression, which is S squared plus 10S divided by S squared plus 10S plus 10. the error can be calculated as the steady state error is going to be the limit when s goes to infinity of s e of s r of s. Okay? This is how we calculate the steady state error. If we apply this here, we find a value of 0.1. Okay? The steady state error is 0.1, or if you prefer, 10%. We are having here 10% of error. Okay? Alright, my friends, this is the video that I wanted to make. I hope you guys enjoyed it and learned from it. I am a teacher. If you want to book a lesson with me, use my WhatsApp number, guys. Goodbye!